All right, folks, welcome. So today we're going to start our unit on machine learning. This is chapter 4 in CE 295 on energy systems and control. And this will actually be a two-part video series. We'll do one part which will take an hour more or less, and the second part will also be an hour. So let's jump in with the outline. First, I'll give a brief introduction to machine learning in this class and the topics that we'll cover. Then we'll get into some details of linear regression and maximum likelihood estimation. I expect that'll close the first lecture. And then the second video lecture will start with time series modeling. We'll go over quickly gradient descent, which will be crucial for understanding neural networks and how to train them. So with that, let's start with the introduction. So the first question you might ask is, what is machine learning? From the perspective of this class, the short answer is simply mathematical modeling from data. So in chapter 1, we talked a lot about mathematical modeling, and most of the perspective in chapter 1 was around mathematical modeling using first principles. So these are commonly first principles that come from physics, such as mechanics or electricity and magnetism, could come from fluid mechanics, Navier-Stokes equations. Electronics, we're using Kirchhoff's current and voltage laws, could come from chemistry, etc., etc. We're going to take a different perspective here with machine learning, and that is, what if we don't have the luxury of understanding well the first principles of our system? Is it possible to assemble a mathematical model from data that we are fortunate enough to have on the system of interest? And that is essentially one of the main ideas of machine learning. I'd also like to make some comments about relationships to other fields. In my mind, at least, machine learning is not a standalone field. In fact, if you review the history and study it, you'll start to understand well that machine learning is in fact a convergence of several existing intellectual fields that are decades or even hundreds of years old. Most importantly, optimization keeps coming up again and again in machine learning. In fact, you could argue that a lot of the techniques in machine learning are applications of optimization. Statistics will play a role as we start to talk about uncertainty. Control theory plays a central role in specifically reinforcement learning, which is one of the sub-areas of machine learning. We won't talk about that in this class. And of course, computer science, in particular when it comes to storing data, manipulating data, accessing it efficiently, so on and so forth. A quick history. So the term machine learning was coined by the famous computer scientist Arthur Samuel in 1959 while he was at IBM. And then a few decades later, particularly in the 80s and 90s, artificial intelligence emerged, and it was a very popular research topic, especially within the realm of robotics. Interestingly enough, during the 2000s, during that decade, AI and machine learning lost its popularity. It seems to me that a lot of this came as a result of two things. One is, well, three things. One, the computational horsepower did not exist that exists today. That was probably the most minor of the three things. Secondly, there was not a strong theoretical foundation on why certain methods in AI worked, which more recently a lot of those theoretical issues have been solved. So the theoretical foundation did not exist in the 80s and 90s. That is on more steady ground today. And the third thing related to the second is there was perhaps hype and overpromised, especially with respect to getting AI to work in certain applications. And now that we have a stronger theoretical foundation, I think we have a more mature idea on how AI and ML can work. So in the 2010s, machine learning and AI has reemerged, and it sort of fits underneath this umbrella that is known as data science. And you may recognize that today, unlike the 80s and 90s, there's a lot of positions out there in industry for data science roles, which includes things in optimization, statistics, control theory, computer science, machine learning, AI, etc., etc. A personal side note, I myself was trained in the 2000s, and in the 2000s, during that decade, my professors, in fact, discouraged me from using machine learning techniques. That was the period where the hype, it was perhaps on the trough of Gartner's hype cycle. There was certainly this mentality during the 2000s that if you're using machine learning methods, that means you probably don't understand well the first principles of your system. And in fact, I think that mentality is a good one to even maintain today. So when you do have first principles, you would like to exploit that. But now we're entering into instances where we might be interested in systems where we don't have first principles. For example, if I send a demand response request to an individual electricity consumer, there are not first principles to explain, well, what are the factors which cause them to reduce their energy consumption or ignore my request. Okay, so now today we can have a more measured approach where we can use data when it's appropriate to build mathematical models and use first principles when it's appropriate to build mathematical models. All right, now a big reason that ML has reemerged in recent years is because the vast and profitable applications in a variety of business use cases. So some applications that are not energy related, but you understand well, you may use these day to day, is, for example, predicting products you are likely to buy. So Amazon is famous for this. This is truly their secret sauce. You understand this well when you go to their homepage. Netflix has algorithms which predict the movies you are likely to watch based off what you have watched and the star ratings that you may have given them. Gmail and other email platforms have machine learning algorithms, for example, support vector machines, which classify your email as spam or not spam. So basically, when your email comes in, they have filters or algorithms that look through it and they look at key features and put it in one of two piles. Is this normal email or is it spam? Classifying objects in a driverless car's path. So for example, if I am a driverless car and I have a camera and my camera is looking forward, from those images I would like to classify objects. And I might wish to classify if I see a stop sign inside the camera's view, or if what I'm seeing is actually the reflection of a stop sign in the window of the bus driving next to me. That's incredibly important to differentiate between those two things to really understand how do I plan the driverless car's path. Forecasting building electricity consumption. So this is going to be what you will work on in homework 4. You're going to build algorithms to forecast residential building electricity consumption. You may wish to predict human electricity consumption behavior. For example, if the utility or the system operator sends a demand response request to a consumer, we would like to understand the factors in which they would respond positively or negatively to that request. Forecasting energy efficiency, retrofit performance. If I do a retrofit on my building for energy efficiency purposes, can I forecast well what the savings will be? Forecasting electricity market prices. This gets into finance. How can I forecast market prices in certain electricity service markets? Forecasting EV charging demand. This is similar to forecasting building electricity consumption, but in fact harder because you're basically trying to forecast when a discrete event happens, charge, don't charge, and much, much more. Now, we can spend a long time talking about the applications of machine learning in general and including for energy applications. But rather than just provide a one-by-one vocational training on how to solve specific problems, my goal with this chapter is really to provide you with a fundamental training so that the problems that we face here in 2018, you may be well positioned as we go through examples to solve those problems, but with a fundamental training, I really hope that decades in advance, as new applications emerge, you have those fundamentals, that strong foundation to attack those problems that occur decades in advance. So that's really my goal, is to give this long-lasting training. So that's why we'll take a more fundamental perspective as we go forth. Now that said, though, let me mention another very exciting success story on machine learning and reinforcement learning in particular. Some of you may have heard of this famous example of AlphaGo. So first, let me talk about the game of Go. The game of Go is a board game, and like checkers or chess, it is a two-player game. But unlike checkers and chess, Go is generally considered to be a much more complex board game. Now, in the realm of reinforcement learning, a lot of the researchers in the past few decades have really tried to understand, can we come up with reinforcement learning algorithms that are clever enough to, from data, from examples of gameplay, to basically figure out how to play better than humans. So the game of Go has been a marker, a challenge that reinforcement learning researchers have been trying to conquer for a while. In fact, we've already been able to establish that a computer can play the game of checkers better than some expert humans. Go is much more complicated because of the complexity of the game. So here you can see a board on the right. You can see all the different cells and the player's different markers, black and white, in these different cells. And so you can understand just by looking at that board that the complexity, the number of states, possible states that could exist, is extremely complex. So a couple years ago, some researchers who are now part of Google DeepMind, who work in reinforcement learning, were able to come up with some reinforcement learning algorithms which actually beat the world champion in Go named LEC10. And this was huge news. They published their work in Nature. In fact, it made the cover of Nature, and really is a great example of what can be done with reinforcement learning. So that's exciting. Unfortunately, we won't have time to get into reinforcement learning in these set of lectures, but we'll provide some of the basic principles for which you can take courses on that afterwards. Okay, so some typical machine learning tasks. I'm going to describe 5 of them here, and regression is really going to be the one that we'll focus on in these lectures. So the first task is exploratory data analysis. And that is exactly what it sounds like. This is a situation where you acquire some data for which you would like to do some mathematical modeling. But before we get into some of the details of certain algorithms or models, we first would just like to explore some general trends in that data. Now, you will practice that in homework 4 with the residential building electricity consumption data. So I won't talk much about that in these lectures. Secondly, we'll talk about regression. Now, regression and classification can be viewed as 2 types of mathematical models from data. The key difference between regression and classification is regression involves mathematical models which will try to predict a continuous variable. The continuous variable might be the electricity consumption in your home. Classification is also a predictive model, a predictive mathematical model from data, but rather than trying to predict a continuous variable, we wish to predict a discrete variable. So this could be spam or not spam for your email. It could be a electricity consumer, and we want to predict if they accept or reject our demand response request. Clustering is a different type of task. The business terminology for clustering would be market segmentation. What this means is I could acquire a lot of data from my customers, for example, their age, what type of products they purchase, where they live, their education level, And then from there, I would like to segment all my customers into a small finite set of clusters or segments. And these clusters or segments might be represented by archetypical customers for which I could provide differentiated services. So that's really the business explanation for what clustering is. And then reinforcement learning is where control theory comes into the play with machine learning in particular. This is a setting where I have some agent that's exploring an unknown environment, and as I acquire data on that environment, I will try to optimize my actions to maximize some cumulative reward as I progress through this environment. And that's what's being done with these board games, right? Is I know the state of the system at this point. I can see the board game. I can see the state of the board at this moment. And perhaps I've been watching my opponent, so I have some idea of typical moves that they might make. I will then plan ahead the moves that I might make, given some knowledge of some inference of what my opponent is doing. And then I will make some moves, and I might do that to explore what my opponent does or try to maximize my cumulative reward, and then take actions in a sequential manner. But in these set of lectures, I'm really going to focus on regression. This is the point which will start and is the typical starting point for machine learning. So let's now dive into linear regression. What's great about linear regression is, in fact, it's not a hard concept. It's something that you may have likely already done if you're in science or engineering. We're just going to formalize this technique. This idea of linear regression, and what's amazing about it is you'll see shortly there is huge value in industry, in fact, to being able to use these techniques. So let me start with a simple example. So suppose that you have data comprised of n data pairs. So each pair is given by xi comma yi, and I have n of them, where I indexes the data pairs. Our objective is to fit a mathematical model to this data. And let's consider something that we all love and recognize, and that is this linear function, or more specifically an affine function, y equals mx plus b. So we have examples, training examples if you will, for x and y, and we have n of them. And from that, we would like to optimally determine values for m and b, the slope m and the y-intercept b, that best fit our data. So this is known as regression analysis. We seek to establish a mathematical relationship between dependent and independent variables, which would be y and x respectively, given some examples, given some data. Now here's a fun side note story. A few years back, a friend of mine, who turns out to be an attorney who works in technology and media intellectual property, sent me a text message. And he said, one of our outside consultant firms billed us $170,000 to do an SQL regression model. And my response to that by text message was, my students would do that for $25 and pizza. And he responded back, yeah, next time we should go that route. And of course, the message here is that simple ideas can have huge value out there in terms of the value that people will attach to them if you can use these methods. So these ideas are simple, but in fact, it could have huge value out there in industry. So anyways, going back to our example, we seek to determine a best fit for m and b in the linear model y equals mx plus b. And we have these example training training examples in the form of n data pairs xi comma yi. So in other words, find the line that best fits the data points in this figure here. So on the x-axis we have x, y-axis we have y, and we want to fit a linear function to this data. All right, now the first concept in linear regression to introduce to you is something known as least squares. And least squares is going to come up over and over again in this chapter on machine learning, so it's incredibly important to understand well. This goes by a variety of names or variations of least squares. It's also known as ordinary least squares or linear least squares. We'll just refer to it as least squares. So we seek to define the best fit as follows. We're going to introduce this notion of a residual given by Ri for a given set of parameter values m, b and a data pair xi, yi. And this residual is going to be defined as follows. It's going to be what our mathematical model predicts. So this will be mxi plus b. This is what we would predict yi to be with our model. And then we subtract from that what our data says y is. Okay? In other words, Ri is the error. It's just the modeling error. Residual is synonymous with error in this case. And for each data pair, xi, yi, we have a corresponding residual for candidate values for m and b. So, for example, if Ri equals 0, that means that m and b fit that particular data pair perfectly in the sense that the error is 0. So, our objective is going to be the following. We seek to fit m, b such that the sum of all the residuals squared are minimized. So we're going to calculate the residual for each pair, and since we're looking at errors, we don't really differentiate between if it's a negative error or if it's a positive error. We just want to send those residuals to 0, so we'll square it so that we're indifferent to the sign. And also, when we square, we can take derivatives and we have differentiable functions, which is important for optimization. So then, mathematically, we can write our problem as follows. We're going to sum up the residuals squared, and then we seek to minimize that with respect to m, b. So if I take Ri and expand that out, then I get the following squared. And I can in fact rewrite that, not with a summation notation, but using matrix vector format and norms, if you're comfortable with that, or you can keep the summation notation. But what's nice about the matrix vector format with norms is that you get this nice clean representation where what we're going to do is assemble this parameter vector theta, which is 2 by 1, which is m and b in a column here. And then you can see that each data pair is going to be given by the following. We take each row of this regressor matrix, as we call it, capital X, and take the dot product of the row of x with column vector theta, and that's going to give us our predicted value for y, which we'll denote by y1 here. And then when we do that for all the rows here, we'll sum that up, or we'll take the square of them, we'll sum it up, and that is the 2 norms squared. Now, what's amazing about this is in this format, you can see, because we finished a chapter on optimization, that this is nothing but a quadratic program. It's a quadratic program in theta, where theta is our optimization variable, and in fact, it's an unconstrained quadratic program. So this is something that we know how to handle well in optimization. So if we solve the QP corresponding to that least squares problem, we then may get a best fit linear curve, which looks like that. So what you can see here is that linear regression is nothing but curve fitting. Curve fitting when we have models that are linear in the parameters. So let me now emphasize that point. Now, in the previous example, we happened to look at a model that was linear in X. But it turns out that this least squares methodology can work for any model that's linear in the parameters. Now, this is an important distinction, so let me pause for a sec and allow you to think about it. What's important is we can solve least squares problems as quadratic programs to optimally fit the parameters of mathematical models when it's linear in the parameters. It can be nonlinear in X, nonlinear in your independent variable, for example, this polynomial here. That does not matter. The important point is that it's linear in the parameters. So let me show you some examples to emphasize this idea. Here we have a mathematical model that's polynomial in x, but importantly, it's linear in the parameters we're trying to fit, the theta i's. Now because of that, we can write the residual as this linear affine function where r equals big X theta minus y, where theta is just a column vectors where we stack our parameters, and then capital X, we, in a clever way, assemble these such that when we take the dot product of each row with a column vector theta, we get basically a prediction for our particular data pair, which will be y1. So you can see the trick here is just really how do you assemble this regressor vector capital X? And the components, the elements of that regressor vector X, regressor matrix X, could be nonlinear in X, as it is here, but importantly, it's linear in the parameter vector theta. Another example is a harmonic model. Here we have functions that are sinusoids. This actually looks like a Fourier series expansion. In fact, it is a truncated Fourier series expansion, where the parameters we want to fit are the weights of each of the terms in this Fourier series. So you can see big X, this regressor matrix, has nonlinear elements in X. You could go further. Here's another example of a Gaussian mixture model where each of the components are some sort of a Gaussian function here, centered at different points, centered at x equals 0 or x equals minus 0.5 or x equals plus 0.5. Importantly, though, it is linear in the thetas. That is the key point, and that's also the reason that I highlight it in blue. So the residual, again, can be written as r equals big X theta minus y, where the theta column vector and the y column vector are always the same in these examples. And basically the trick is, how do you assemble this regressor matrix big X, which could have nonlinear elements in X. So this is limited only by your imagination. You could come up with all sorts of linear in the parameters models, and they are equally easy to fit in the sense that you can formulate the optimal fitting problem as a least squares problem, which turns out to be a quadratic program in the jargon of optimization. Okay, so let's generalize this from an optimization perspective and recognize that all these linear regression problems for linear in the parameters models can be written as the following QP, where we want to minimize, with respect to theta, that's our optimization variable, the 2 norm of a residual squared, where the residual is going to be given in a vectorized form by big X matrix multiply column vector theta minus column vector y. We take the 2 norm of that, which means that we take each of the elements of the vector, square it, sum it, and then the 2 norm by itself would take the square root of everything, but we square that, so we just take the elements squared and sum them up. That's it. Okay, now X, our regressor matrix, is generally n by p, where n is the number of data pairs we have, and p is the number of coefficients or parameters or weights that we wish to fit. And typically, we have a situation where the number of training examples n that we have is much greater than the number of parameters that we wish to fit. This turns out to become an overdetermined linear system of equations. That's actually another way to look at this mathematically from a linear algebra perspective. We have more equations than unknowns, so it's an overdetermined system, and so we'll use least squares to solve it. So with that in mind, that's actually going to give some intuition for the solution to this. Now, interestingly, because it's a QP in this least squares format, we don't even need to use an optimization solver package to find the optimal value for theta. It turns out that there's just one simple formula, and we can derive it quite easily using the first order necessary condition. So recall from chapter 3 on optimization that if theta star minimizes this QP given in equation 10, then what that means is that theta star must satisfy the following equation, which says that the gradient of my objective function with respect to my optimization variable theta equals 0. I take the derivative of my objective function, and that should be 0 at theta equals theta star. So we can expand this condition. So here I'm just rewriting that condition. And then in the second line here, all I'm going to do is rewrite this 2 norms squared as the inner product of this vector. It's just another way to write the 2 norms squared. And then I'm going to expand out this product. Now, if you're like me, then you learn the FOIL trick, first, outer, inner, last, as a way to multiply out this product. So here we do, we expand this, being careful to note that we're working with vectors, not scalars here. And now I'm finally going to take the derivative of this expression with respect to theta, and we get the following equations on the second to last line. These are sometimes called the normal equations. But now what we want to do is solve this with respect to theta. And now I get the following formula. So amazingly, to solve the least squares optimization problem is one simple formula, which just requires some matrix arithmetic. Not even matrix algebra. We just evaluate this formula, and this is the formula for theta star for the least squares problem. Okay, as a side note, you may also recognize that this is the formula for the so-called pseudo-inverse, or the Moore Penrose pseudo-inverse to be specific. You may have come across that in a previous course on linear algebra. When you're solving an overdetermined set of equations, you have more equations than unknowns. If you haven't seen that, don't worry about it. You can just memorize this or remember this formula, or recall that there is a single formula. But if you have seen this before in linear algebra, I think it's nice to mentally make that connection. Okay, so now I want to talk about a very popular variation of least squares, which is least squares with L2 regularization, where L2 refers to a norm. Okay, that's a lot of mathematical jargon. Let's break this down in an applied sense. Now, what if we define the best fit by a different criterion? For example, suppose that, indeed, we're interested in minimizing the sum of the residuals squared, but if we do that by itself, we could end up with solutions where the coefficients, or these parameters, get too big in magnitude. For example, we might get parameters that are 10 to the plus 14 for some parameters and are 10 to the minus 14 for other parameters. And that can be problematic for a model or for data collection or for accuracy calculation reasons. So suppose that we would like to provide some sort of, we call it regularization, to make the parameters not extraordinarily big. So the idea here is that we're going to take our least squares objective that we've seen before, and we're going to add a second term which penalizes the size of the coefficients in my parameter vector theta. And we're going to represent that mathematically by the 2 norms squared. Okay? And this is called L2 regularization, which refers to the idea that I'm going to add to the cost function some sort of norm on my optimization variable. And in this case, it's going to be the 2 norm, which is why we call it L2 regularization. And then alpha is a parameter that we pick, which says how much do we care about minimizing the residuals squared versus how much do we care about making these coefficients small in magnitude. So you'll of course notice that if I pick alpha equals 0, then I just get my pure least squares or ordinary least squares solution. Now, amazingly, the formula to solve this problem is also very simple. And we can go through this using the same technique by applying the first order necessary condition, where we take the derivative of the objective function with respect to theta, set it equal to 0. So here I'm taking the derivative of my entire objective function with respect to theta. Like before, I'm going to expand out the 2 norm. Then I'm going to expand out this multiplication using the FOIL technique. alpha, theta transpose theta, is going to collect with the first term. So then now I have this slightly modified coefficient, which looks like x transpose x plus alpha I, where I is the identity matrix. Then, when I solve these so-called normal equations for theta, I get theta star equals the following, which looks very similar to the formula for pure least squares on the previous slide here, except now x transpose x is modified slightly. I'm going to add to it alpha times the identity matrix. Now this is quite interesting because now when I show this equation, there's another interpretation which you can have if you wish for L2 regularization, and it's the following. Now, if we go back to ordinary least squares, you'll notice here in this formula we have x transpose x, and then we take the matrix inverse of that. Now, when we invert a matrix, flags should go off in your head to related to the issue of, is this matrix invertible? So sometimes we may get a set of data where x transpose x is not invertible. Okay. Now, when it's not invertible, that means that this inverse operation is poorly conditioned in the sense that when you take this inverse, well, ultimately what's going to happen is you're going to have values of theta which will change by orders of magnitude. And that's actually a function of the fact that you have poor data in the sense that x transpose x is not is close to being non-singular, is close to being not invertible. In fact, one way you can measure that is with a condition number, which is given by the ratio of the max and min eigenvalues. For example, in MATLAB, you can do COND and then give to that function x transpose x. So what L2 regularization does is it better conditions the inversion of x transpose x by adding to it a diagonal matrix where the elements on the diagonal are alpha. And that better conditions the data for least squares fitting. So it's a way to handle robustness. Now, why would you get data for which x transpose x is nearly not invertible? Actually, another important interpretation of that is it means you have data or a model structure such that you are unable to uniquely differentiate between two parameters. Mathematically, if you get non-singularities with x transpose x, that's what it means, is that you are unable to uniquely differentiate between two parameters. So that means you have a problem with your data. It is not sufficiently rich in that sense, or your model structure is such that you are unable to differentiate between two parameters. So L2 regularization is one way to just kind of work your way through it without changing your model or data. But if this comes up, then you may actually also want to relook at your data or your model structure. Okay, so here's an example where what we're showing is the, I should go back and also mention that least squares fitting with L2 regularization is also known as ridge regression. That is a name that was given particularly in the computer science field. If you use Python and scikit-learn, you'll recognize that this is actually the ridge function. That is jargon, actually, that I think is not helpful for fundamentally understanding what least squares does. As you'll see, these different fitting algorithms are basically least squares with different types of regularization. So for me, at least, I think it's better to think about it as least squares with L2 regularization. And as a side note, note that this is called ridge regression as a specific jargon used especially by the computer science field. Okay, so here's an example of these so-called ridge coefficients, these optimal parameters, as you vary alpha. Now remember, alpha corresponds to how much you care about making the coefficients small in magnitude. So on the horizontal axis, we have alpha, and okay, the horizontal axis is a bit odd. We are increasing from right to left. Okay, so all the way on the right side is when alpha is very small, and all the way on the left side is when we increase alpha. Now, On the vertical axis, we have the values of the parameters theta, or the weights here. So if you make alpha essentially 0, like 10 to the minus 10, then you can see that the values of these parameters, which are given by these colors here, vary quite a bit in terms of their magnitudes. As we crank up alpha and move from right to left, what it has the effect of doing is saying, okay, I want to, I care a little bit less about minimizing the residuals and a little bit more about making the magnitude smaller. And if you keep cranking up and up, you'll in fact send your coefficients to 0. All right, so this just helps you give intuition on what the optimal parameters look like as you increase alpha from right to left. All right, let's now talk about a different regularization method known as L1 regularization. So let's now define the best fit by a different criterion. For example, suppose that our data occasionally contains outliers that can bias our fitted linear model in some undesirable way. And this happens all the time when we get data in data science applications. We might get some data readings where they're just erroneous and they have some values that are nonsensical. So is there some sort of robust regression method that will try in some sense to de-emphasize the effect of these outliers? And the short answer is yes. One way is with L1 regularization. So here's what it looks like from an optimization perspective. We have our typical least squares objective where we minimize the sum of the residuals squared. And now we have a regularization term which looks similar to the one with L2 regularization, except now instead of a 2 norm on theta, we have a 1 norm. Okay. Now recall the following definition for 1 norm. In fact, let me flip over here to Photoshop where we can draw it. Okay, let me do it like this. So the 2 norm is going to be given by, whoops, let's maybe undo that. All right, is going to be given by the following formula. We're going to sum all the elements of this vector theta. We're going to square all the elements of vector theta and then sum it up. And this is the 2 norm, and in fact, we will then take the result and take the square root of it. Okay? This, in fact, you can recognize as like the root mean square. That's what the 2 norm is. Now, the 1 norm is given by the following formula. So again, we're going to work with the individual elements of theta. There could be n of them. And we're going to sum the absolute values. Okay? And that is the 1 norm. In fact, the formula for the p norm, just as a bit of background, looks as follows. So the p norm is given by the following formula. Okay, we are going to take the elements of theta I, put them to the power p, and actually take the absolute value of this. All right, and then the full result will then take to the full power 1 over p. Okay, and this is the p norm where p can be 1, 2, etc. And this is the definition for p norm. So L2 regularization corresponds to this one, the 2 norm. This is ridge, in the parlance of computer science, ridge regression, and then L1 regularization corresponds to regularization corresponds to this one norm here, and in the parlance of computer science, they call that lasso. All right, I'll mention what lasso means a bit later. So if we think about this, the key difference here is L2 penalties place a small weight on small coefficients because we're taking squares instead of the absolute value. In other words, theta I squared is very small when theta I is small, and because of that, there's little incentive to derive theta I to 0 unless you consider the absolute value of theta I instead. Okay, so it's really going to be helpful if I draw a picture of this. All right, so okay, the horizontal axis is going to be theta I. And then now what I'm going to plot is the absolute value of theta I, which might look something like this. Okay? Now in contrast, if we're minimizing the square of theta I, this looks like a quadratic as follows. Now, the key concept here is that when the theta i's get very small, if you use the 2 norm, then the penalty you pay is quite small. So there's little incentive to take theta I all the way to 0, because when it's quadratic, even if you're close to 0, the penalty is vanishingly small here. In contrast, with the absolute value of theta I, there is still relatively large penalty even for small values of theta I. So there's more incentive to take theta I and send it to 0. Now that has an important interpretation in application for L1 regularization, which we'll see here in a sec. Now note here, because our objective function involves a 1 norm and the sum of absolute values, this is no longer a quadratic program, but it is a convex program. So we cannot solve this using quadratic programming solvers, but we can use convex programming solvers like CVX or CVX-Pi to solve this L1 regularization problem or this lasso regression type of problem. So let's go through an example so you can gain more intuition for what L1 regularization is doing. So I'm going to pull up an example of from homework 1 on batteries. So here what I'm showing you is some measured data, this is real world data, of the open circuit voltage or the relaxed voltage of a battery cell. So you can see here it's got this property where as the state of charge increases from 0% to 100%, it generally increases, but there's this long kind of flat region, and then there's shoulders at the extreme region here. So our objective is to do something simple that we encounter in science and engineering all the time. I get this data, I just want to fit a function to it. That's it. I want to fit a polynomial, for example, this 8th order polynomial here, where the unknown coefficients are going to be theta 0 to theta 8. So there's 9 of them because it's theta 0 to theta 8. So if I formulate the least squares problem, which is a QP, I can come up with a fit to my data, which looks like this dashed black line. And what I'm showing here on the bottom is what the coefficients, what the parameter values will be from doing this least squares fit. Okay? Now next, we're going to look at what is the effect of applying L1 regularization. And this example is important because it's going to give you some intuition for what is the power or what is one of the use cases for why we want to do L1 regularization, also known as lasso. Okay, So now what I'm going to do is do L1 regularization with some small value of alpha. So what this says is I care just a little bit about penalizing the magnitude of my coefficients using the 1 norm, absolute values. So here I've got some pretty small value of alpha. Now, interestingly, when I solve that L1 regression problem, you can see the results look as follows. I have my optimal coefficients here, my parameter values, but interestingly, theta 4, theta 5, theta 6, and theta 7 go to 0. So what that means is what it's doing is it turns out that I can reasonably well approximate this curvy voltage curve by a polynomial where I don't need the 4th, 5th, 6th, and 7th order terms. So what's cool about this is lasso has the property of selecting which parameters are more important than others. And what it's doing here is it's saying theta 4, theta 5, theta 6, and theta 7 seem to be the least important in terms of fitting this voltage curve. So that's pretty neat because then although I was interested in fitting an 8th order polynomial, what this result says is if I sacrifice a little bit of accuracy, and I'm okay with that, then I can get away with a polynomial which just has the 0th order term, the 1st order term, the 2nd order term, the 3rd order term, and it turns out this 8th order term as well. So lasso actually stands for least absolute selection operator. There's another S in there, and I forget what it stands for. Part of the reason I don't recall is because I think it's much better to remember it as L1 regularization. So excuse my ignorance on the jargon of what they use in computer science. But the effect here is that it selects which parameters are the ones you wish to keep. So now if I crank up alpha, let's continue this further. You can see it does more to mute out certain parameters. In fact, it just keeps the 0th order term, the 1st order term, and the 3rd order term, which is saying that this voltage curve is relatively well captured in shape by this cubic. Okay, and then I can go further. I can push it even further. This is the best linear function that will fit this curve. Okay, so these are all the results from the previous slide superimposed on each other. And where we have L2 regularization where alpha equals 0. Sorry, this should actually be L1 regularization. All of these are typos. And you can see the results here. So indeed, when you... Oh, I'm sorry. Excuse me for stumbling here. This is actually... All right, these previous slides are the results with L1 regularization. These are results doing L2 regularization, where I'm penalizing the magnitude of the coefficients with the L2 norm. So no error on this slide. The point here is you can see that as I increase alpha, I degrade a little bit my resolution, but here I can make the parameters smaller in magnitude. So depending on your application, you may want to apply these regularization techniques. Okay, now with that, we can then talk about a generalized linear model. So the generalized linear model is given as follows, this linear in the parameters model. I have some output that I seek to predict, which is scalar in this case. And it's given by a weighted combination of these regressors. We'll call it phi of x. And phi of x, I want to emphasize here that phi of x could be nonlinear in x. It could be polynomial in x. It could be sinusoids. It could be these Gaussian functions. It doesn't matter. The important thing is that the weighted combination of these regressors is with these coefficients theta. And we can write this in a clean linear way using a vector notation as theta transpose phi of x. And then with this, we can then fit these parameters theta using various least squares method. So the summary of the regression procedures is you can use just ordinary least squares, LSQ, also known as linear least squares or ordinary least squares, and it turns out from an optimization perspective, that's a convex quadratic program. You can use least squares with L2 regularization, that's also known as ridge regression, in the jargon of computer science and scikit-learn. This also turns out to be a convex QP, very cool. Least squares with L1 regularization is also known as lasso regression, which kind of has this cool effect of selecting which of your regressors and which of your parameters are more important than others. So that's quite neat to basically do like a model reduction, if you will, to find what is a possibly smaller model, a less detailed model, which fits well in my data. Now that is not a convex QP because the L1 regularization terms add these absolute values to your objective function. Absolute values are not quadratic, but they are convex, so that is a convex QP. And then these last two are mixes of those concepts. I didn't talk about them in detail, but because you take an optimization perspective on it, it turns out that these are just convex programs as well. So there's some mix of doing, if you did both L1 and L2 regularization, you had both those terms in your objective function. In the jargon of computer science, they call that an elastic net. Okay. But I think if you view this from an optimization perspective, you can just say, oh, I take a 1 norm and a 2 norm and I add them and that's it. Then there's this idea of a hybridized L1 and L2 norm, where you kind of create this hybrid norm, which has features of the 1 norm and the 2 norm. They sometimes call that robust least squares. That is also sometimes called Huber regularization. It goes by many names, but I think what unifies all these methods, instead of remembering a bunch of jargon that varies from field to field, is just understanding well what is the cost function, right? So we always have this least squares term and then various types of regularization. Okay. The final piece I want to talk about is maximum likelihood estimation. And actually, I think what I'm going to do is I'm going to pause here and stop this lecture, and we'll pick this up next time.